Today, I want to talk about an extremely dangerous supply chain attack that happened. This was called TJ Actions, but as we dive in here, we're going to really notice that it was a lot more than TJ Actions. And there's a few things I want us to take away. First is how to defend against these kind of supply chain attacks. And second is really how interconnected everything is. And honestly, how scary a lot of these supply chain vulnerabilities are. Frankly, the root of it is a couple things that I've written about. That first, GitHub doesn't give us enough access to security reviews, to security logs, to security data to try to make decisions about open source. And second is that even if they did, a lot of people don't pay attention to it. And you end up in these sort of interconnected, giant worst case scenario messes. And that's what happened here. So I just wanted to go through a high level overview first of what happened. First, it's been shown that this thanks to a lot of research from the Wiz team, from Unit 42, which is Palo Alto's team, but just a lot of different people were also working on it in the open source community. So first, there is this repository called ReviewDog, and ReviewDog is fundamentally used to create comments based on logs that run. So like you run a test scan and you want to get the results back to a developer, you would use ReviewDog to do a comment on the pull request, for example, to do it. And the problem is they had an automated way of assigning permissions to people in order to allow them to merge pull requests. So that automation was exploited by an attacker in order to gain push access to the repository. But first what they did was fork the repository and then added a malicious commit and open a pull request. And so what this is, when you fork a repository and open a pull request, that can create a commit that's never actually, even if the pull request is never actually merged, it's part of that Git branch's history. And since it's on the history, it means that it can be referenced by tags. And so this is fundamentally the way that most of this attack happened, was the attacker not going in and like merging to main, but instead going into these releases. And you can see how this release here is pointing to a specific commit. And changing this commit ID is a lot easier and less, there's not even a GitHub log for it. It's a pretty under the radar activity because obviously people aren't like memorizing these commits. So the attacker gained access to change this commit and was able to point it to their orphaned commit, which is what it's called when a commit gets left behind, not attached to any branches. It's just there and exists. And so they use those elevated permissions to push a tag referencing back to their malicious commit. And using that, it was clear that they were actually targeting this TJ Actions ESLint changed files. And the TJ Actions repo is really funny to me, first of all, because it shows the impact that just single people have in this ecosystem and how we take it for granted. I'm pretty sure it seems like TJ Actions is run by one person who I've actually talked with, and he's a cool guy, Tanya. Just a reminder that sometimes you are using a piece of infrastructure maintained by one person who is unsponsored, not making any money, and honestly doesn't owe you anything. And so it's just a reminder that how all of these things are connected. So the attacker gets access to a key by having it print out in the workflow log. So I have an example of this here where I made a GitHub action that specifically generates a bunch of fake secrets. And you can see how these aren't super obvious. Like even within this where I'm like specifically saying that I'm generating them, like I have to click into the logs to see this, and then they're base 64 encoded, which is not a real security mechanism, but it is an obfuscation mechanism, right? By looking at this, I can't immediately tell, oh, that's a secret. And so people aren't manually checking these a lot. It's a pretty smart way to try to exfiltrate secrets from repositories. And so the attacker, that's what that malicious commit did, was it made it so that in the GitHub action workflow, it exfiltrated any secrets that were being referenced. And what that looks like is when you have workflow files here, you can see here where I'm referencing in this workflow, for example, my Docker username and Docker password with a secret. And so the attacker essentially just made it so they accessed the memory of the working job and they printed these secrets out to the logs. And so they did that in order to get an elevated token to TJ Actions. And then once they were in there with the TJ Actions bot account, which is just a bot account that Tanya was using, they went to phase 2, which it's clear was actually targeting Coinbase, which makes a lot of sense because a lot of why this initial attack didn't make a ton of sense was it was very high level, where essentially the malicious commit that we saw initially was just printing out secrets from every public repository that was using this TJ Actions changed files workflow. And what this GitHub action did, the changed files one, was just create a list of referenceable variables for what files had changed between commits. A super easy little use case that it did. It was used in a lot of different public repositories just to make that a little bit faster. So you can see that this earlier commit that initially wasn't identified was explicitly getting if the GitHub repository owner was Coinbase, then go ahead and run the script to print the logs. And so the first version of this attack was actually targeting specifically Coinbase. And Coinbase, it'll be interesting to see when they publish it, if they publish a review to say how they detected it and responded so quickly. But at the end of the day, there were no secrets that were compromised as a result of it. They deleted the workflow logs and they cleaned it up. And that's when the attacker broadened their payload to dump secrets across the ecosystem, so it wasn't targeted anymore. And then at some point, the attacker, these initial accounts that were used to compromise the review dog, we don't know when this happened, but they changed the email addresses associated them to an anonymizer or an obviously fake email. And then GitHub, when that happens, apparently removes all of the commits and public profile of the user. And it makes it even harder to try to detect what happened. And I just wanted to point out how crazy this is, that there's this project GitHub Archives that's a giant archive of everything that happens in GitHub. And if it wasn't for the logs that were stored here, we really couldn't have investigated most of this. And it just points to like how bad the GitHub logs are from a security perspective. But we'll get to that. So once the attacker broadened the payload to anything, that's when we noticed, hey, if you're using this version, these affected versions of the TJ GitHub action, it is downloading a script and printing all of your secrets to the GitHub action. So now that we understand what happened from an attack perspective, I want to talk about some ways that we can detect and prevent this sort of stuff in the future. And unfortunately, a lot of it is on GitHub side from the open source compromise part. But there are 4 general things that you should do that would have prevented a lot of this from happening. The first is pinning GitHub actions. And to show an example of what that looks like, you can see here when I use Amplify, for example, I just say, check out the Amplify security action runner at main. And instead, what I should be doing here, and instead of saying at main, I should look at the latest commit. I should copy the commit SHA back in here, edit it. And then instead of at main, it should be at that commit. Go ahead and just commit that because it's an example of what should happen anyways. I'll make a new branch and call it Amplify Pat. And so by doing that, I made it so that even if so pretend this Amplify security repo were to ever get compromised, someone were to change the code, change the latest on main, I would automatically just inherit those changes as soon as they happen. And instead, I want to make sure that, hey, I know that this is in a good state right now, and I need to pin my GitHub action to it. Now, it's totally worth pointing out why people don't do this, and it's because it's super annoying. Because now, anytime I want to update this workflow because, say, something changes in the background, or they do a security patch, or they do something else, I need to come in here and do that manual process again and again, unless I do some creative scripting with Dependabot or some other services to do that. I wanted to show this. One of the cool things that Aikido Security does is when they detect that you don't have an action pinned, they actually create auto fixes that go and look up what the latest commit SHA is for you and then create the PR. And so what's funny is this auto fix actually fixed an issue I had where it defaulted, the default branch for this is development instead of main, and I just didn't notice that. So I would have actually been copying the wrong SHA, but here Aikido is able to even look up and see, okay, this is the one that you're looking for. It's in the main branch and it's the latest one. And so this is a nice way, it's a nice feature that they have to automate that pinning process. But that's the first piece, is pinning GitHub actions. The second piece is signed commits. And so throughout this attack, it was very common for the attacker to impersonate a different user. So here we see the malicious commit, and it looks like it's coming from this guy who is a Coinbase employee, probably. Yep. And this is super easy to do. I don't know if people really know how common this is. So all someone has to do in order to impersonate another user in GitHub is run these 2 commands. The first is to set a username, and the second is to set an email address. And if this matches a real user in GitHub, it will automatically show that person as the one who made the commit. And the way that you fix this is with verified commits or with commit signing. And so you can see here, just even in this repo I had open, the verified ones are the ones coming from a signed commit. And the unverified means that it wasn't from a signed commit. And again, people don't usually bother to turn this on just because it's annoying. In order to set it up, you have to set up GPG keys, and those are confusing. So it does require changes on the developer side in order to turn it on. But without turning it on, you can't trust the identity of any of the commits that happen. And so here in my repo, you can see where I bothered to turn it on, and there's been times when I've pushed from my home desktop where I have the GPG keys configured, and I've pushed from other devices where I didn't have it configured. And really what you need to do is turn on verification signing, especially for merging to main, just as a way to guarantee that an identity is tied to who it is. And the way that I think of this is more like device-based authentication, where you're really just proving that, hey, I know the device that this is coming from, because in order to set this up, you go into your GitHub settings, you go into your keys, and then within the keys, you can see the key ID, and then the private key is on my desktop, and that's what allows me to authenticate and validate my user. And so if I was ever setting up another device, the way I would have it do verified keys is either to create a new GPG key and add it here, or to copy the private key from this onto my laptop, and either one of those would really work. And really, this vigilant mode is very cool too, where you can, anytime that my account would get used, I can make it, hey, it's going to show unverified whenever it's not a signed commit. And so if I go back here now, you can see that it's saying unverified to make it a little more obvious that it is not a verified commit. It could have come from really anybody. So that's the second thing, is signed commits. If that had been turned on, a lot of these actions can't happen because a privileged access token can never sign a commit. And so I want to get into that now, because a lot of this had to do with who had access to change the tags on a repo. And that's where the access tokens come in. And again, that is set under here, under your developer settings. You have personal access tokens. You have fine-grained tokens, which are annoying and people don't use them as much. And so people go back to the classic tokens. And for here, you can see how easy it is to set these tokens and forget that you've done it. And when you're generating them, it is very easy to make them, I'm not going to go through that process, but when you go through it, it's very easy to make them over-permissioned. And it's important. First, there's a kit from ChainGuard that has come out called OctoSTS. And this is like a self-hosted GitHub app you can do. And what this does is create short-lived access tokens based on trust relationships. So you can validate, like, this is a GitHub runner that's authorized, and it's going to fetch a short-lived access token. And that would really be ideal. But it's a lot of setup that a lot of people probably aren't going to want to do, which is unfortunate because GitHub doesn't have a way to do this more organically. And so instead, I think what's helpful is for people to start monitoring these access tokens more. And again, unfortunately, since the GitHub API is such a pain to use and everything's frustrating, I wanted to show another tool called Vorlon that a lot of what this tool does is they take a more active approach to monitoring things like OAuth tokens, access tokens, third-party tokens. And again, this is like a category of tools called NHI. It's not just them that does some of this, but I think they do a good job showing some of it. So here's an example alert where you can see things like whenever there's a new secret that's detected, a new OAuth endpoint created, things like that. They're hooked in and reading the logs. And so here we have a new unknown source IP. And this source IP would be where when you see a change in source IP, that's outside the GitHub ecosystem. So pretend we're the TJ Actions maintainer and we're using our TJ Actions bot. That thing should only be running within GitHub or my personal computer. And those IP address ranges are going to indicate a good geolocation or be known with GitHub. But instead, if all of a sudden it starts coming from another country or it starts coming from somewhere else, it's going to be pretty obvious that, hey, there's something unusual happening here. And so within this, I'm able to see, hey, it's a threat IP. It's flagged by different security vendors. I can look at the traffic and I can see, hey, specifically, this access token was used to create a pull request. And so this is exactly how this would show up when it comes to log monitoring. And again, you can do some of this manually if you were to try to point your GitHub enterprise logs to a SIM and create a lot of this detection engineering yourself. But you can go in here and see, hey, this is a fine-grained personal access token with the object name, what IP address did it come from, all of that stuff. And if we look at that token itself, we can see all of the permissions that it has, what fields it has access to, and even what relationships it has. So who's been using it before and who do we know is okay to use it versus what's the entity that it came from. And then we can revoke the access token from here. So yeah, there are a lot more tools in this NHI category that are to help monitor for these privileged access tokens. And I just wanted to show an example of what those look like. And that would have been helpful for, say you were Coinbase and maybe they were doing something like this, and your access token was logged to the GitHub Actions log. You would immediately be able to see if someone else started trying to use that token in a way that was unexpected or unauthorized. And the final piece is that runtime monitoring. And for that, there's a few different approaches out there. The first is there's monitoring the GitHub Actions logs themselves. This is something that I've never even really thought to do all that much. And the idea of sending these logs somewhere, you can download the full archive or view the full logs. And so you can get all of these logs out and try to make sense of them. Obviously, doing that manually is not going to be a super fun experience. As part of this attack, I created a little script that allows you to do a search to see if you've been impacted. And all this does is allow you to quickly check your check your logs for secrets. And so here I will scan mine, and first I have to log in. So all this does is manually download and check a lot of your most recent GitHub Actions logs. You can also set it to look for the specific dates of the attack, or you can do a full scan, which is just heavy API usage, but it goes through and actually checks every single GitHub action log, whereas by default, it just looks at the 5 most recent for every workflow type. And so here it is searching. I have 5 repositories that are public, and it went through all 5 of those, and it detects secrets, and then it checks for base64 encoding, and then it checks for double base64 encoding, and then it runs a secret scanner against all of those, and then it saves the results to here. And so this is why I created that like test repo where it's showing me the encoded value, the decoded value, and then where to go to actually get the log itself for what was happening. And so this is a handy way to just check if you were affected, if you have public repos and you're worried about it. But outside of that, there's the runtime monitoring piece. And when it comes to monitoring for these sorts of attacks on GitHub runners, it can be super noisy. And so one of the companies that discovered the initial attack was called Step Security, and they detected it because they saw an unusual DNS egress call from the CI/CD to the GitHub gist, and that indicated that an anomaly had happened. And the challenge with monitoring these environments with a lot of different eBPF tooling is that the nature of the workloads is always changing because they're building new code bases that have different requirements. And so there can be a lot of noise that's happening in the environment. And so it's really hard to test for. And a lot of people don't monitor their CI/CD runners. And so there's that approach. There's a company called SciCode, has a tool called Simon that is a eBPF agent built to run inside your build process. But I wanted to show just testing the attack with Sweet Security here, because I think they did a really good job like breaking down everything that happened as I was doing the test. And they automatically summarized it as a memory dump attack and really saw, of all the tools that I tested, there were a bunch of them that did detect it. So this memory dump attack that happened, just for clarity, this is when it reads the process ID of the GitHub action and then it dumps all of the memory out to an output. This gives an attacker access to all the secrets of a running process. And so this is an extremely common way to try to get application secrets because you can read everything that the application has access to. And I just really liked how here you can see exactly what happened. Where I went in, I had to install sudo in the first place because I didn't have it on this pod. And then I ran a GitHub gist. So I created a memdump.py, and you can recreate all of this yourself. In my article here, I have a payload where all I do is I curl this Python script and then I run it. And all this Python script does is grab any sensitive process name or the first process, and then it dumps the memory out to standard out. And so it's not a complicated script, but it's exactly what the attacker did. And so my goal was to see, hey, what eBPF tooling would detect this sort of attack that was happening. And what's important about it is how it ties together not just the memory dump that happened, but also that, hey, there was a curl, the script URL is changing to evade detection, and then you're seeing this additional like base64 encoding that was happening, and then the memory access. And so all of this is meant to show, hey, you can see the curl command to the gist, you can see that the Python script runs, and then you can see the foreign memory access. So I really liked how Sweet broke down all of these different pieces of it to make it just super clear what happened. Because a lot of times when you use these tools, it can come across as just like memory dump or token accessed, and it's so hard to tell what happened. But this breakdown, yeah, I was just super impressed by it and all of the commands that I ran in here. As you can see me trying different versions of the script to try to get it working. The final thing I want to talk about before summing up is really how a lot of this is on GitHub to fix, because a lot of what I wanted to do was go and support the maintainer of TJ Actions, because it seemed pretty obvious that it was just one guy who it seemed like he was probably getting just blasted with a bunch of different requests and different security issues. And I wanted to go support him, but the problem is he had no way to prove, first of all, that he's a real person, that it's a real maintainer, that it wasn't him that did the breach himself, that it was a compromised token like he was saying. The problem is the security in GitHub just doesn't have a way to actually verify that. And just as an example, say you're using my test repo to test somewhere, like you're assuming that I have a lot of security settings turned on and branch protection, but you have no way to actually validate that. For example, I saw somewhere where TJ said that he had signed commits turned on, and I couldn't figure out if that was like before or after the attack. And it had to have been after, but it's just the problem of there's no way to validate anything, and that's such a problem. So I think GitHub should create opt-in ways for maintainers to share more security data about what's going on with their repo so that different people and vendors can create ways to automatically deal with some of that stuff. If you want to protect yourself against this stuff, the first thing to do is to pin your GitHub actions, like we talked about, to commits instead of versions. The challenge with that is you have to be confident that commit itself isn't already have compromised code in it. And that's just like an open source trust thing. It's probably fine. Someone probably would have said something. But what I get really freaked out by is how much we like stumble into these detections. If the attacker had used github.com instead of just.github.com, it's unclear to me that step security would have caught it in the first place. And then the attacker would have just kept doing their thing. And so I have huge concerns about the visibility that we have in when these supply chain attacks are even happening. XZutil similarly was just detected by a guy who was doing SQL database baselining and saw that performance was out of whack. Otherwise, we wouldn't have seen it. So I'm hugely concerned about already compromised code. But all that to say, pin your GitHub actions, work towards signed commits or turning it on. It is so important that you can verify people's identity when they're pushing code because it is so easy to fake people's identity in Git. And the problem is that just how humans work is we trust identities, right? If I see that my boss is the one who committed a piece of code, or I know, hey, this security architecture guy, like this is the service that he owns, he's really the subject matter expert on it. I don't understand what this piece of code does, but I'm sure it's fine because the tests are passing. I'm going to go ahead and approve it. That is a very common thing. And signed commits are just an easy way to, not easy, but they are the easiest way to try to prevent that spoofing that can happen and take us off guard. Like it's basically phishing for developers. Third, monitor your privileged access tokens. This is a really difficult thing to do yourself, but it's possible. There's a whole category of NHI, non-human identity security vendors that would love to help you out with it. But yeah, even more important than monitoring them, having a plan for what tokens are allowed, when should they be used, all of those things are important. And then finally, consider the runtime monitoring of your workflows themselves, of your CI/CD runners. How are you doing it? And all of that. So hopefully this was helpful. Thanks for hanging out.